Will the fun never end? It feels like it won't, huh? More max and min values. This time we're going to start dealing with this idea of a critical number or a critical value. They're critical, believe it or not. Typically we're going to be using them for one purpose, but there's actually two things that occur with a critical number. So let's go get it. There's our max and mins. Keep going, keep going, keep going for mas, and bang, there we are. We're at our critical numbers. They're critical. Let's read through it. So the first this part of the sentence is just kind of taking care, it's covering its ass. We'll be back to it. So a critical number of a function f is a number c in the domain. So it's just some number that's in the domain. That's really what it's saying. Just some number has to be in the domain of the function f, such that, and here's what it's saying. So if you number that's in the domain, we'll call it a critical number if when you plug it in the derivative equals 0, or the derivative doesn't exist. So two things. All the values that you can plug in that are in the domain of the function, domain, all shit you're allowed to plug in, that makes either the derivative equals 0 or that the derivative does not exist. So let's see some problems. I think really seeing this as an example. So this is actually getting into much more of like homework problems. You've seen a lot of theory so far, and I imagine it's a little funky. But now we're going to get into some actual exercises or problems. So I've chosen 2 out of your text. I think they're pretty good ones from our Stewart text, our 8th edition. Shows number 38 out of 4.1 and number 42 out of 4.1. So why don't we start off with 38. And we're going to want to find 2 things, right? We're going to want to find where the derivative equals 0. Notice I'm writing x. I'm just writing x. And where f prime of x does not exist. Getting a little sloppy about it. Maybe change the color up on that one so we can see 2 different things. All right. So let's take our function. So it says derivatives. We're in calculus. Shit, let's get after it. Let's go take a derivative. But first, let's get this derivative friendly. You know? Get rid of that radical. Let's put that into some rational exponents or fractional exponents, wherever the hell you want to say it. Oh shit, why'd I put prime? It's not a prime. No, I did with some algebra. I'm so excited to do calculus, I was already writing down the prime. Okay, now let's take a derivative on this sucker. We take a derivative on x. Our 1/3 falls to the front. We rewrite the interior. We subtract 1 from 1/3. That's negative 2/3. And oh shit, don't forget about the chain. The derivative of 4 minus x squared. That's negative 2x. Now in the past, I've told you I've been pretty lenient about the idea. Hey, you want to leave negative exponents? Sure, I don't give a shit. Just leave your negative exponents. Don't want to clean it up all the way? Don't clean it up all the way. But this is now the time where if you don't understand what the hell it means, you're screwed, because we're going to have to start setting things equal to 0 and solving. We're going to have to find out what's not the domain. A lot of stuff going on. So we look at our original problem. The domain's good. Okay, then we go through, let's clean this up. Let's start setting it equal. So the only thing that stays up top is that negative 2x. Everything else goes down below. That 1/3, the 3 is down below. And let's just get rid of that negative exponent. So the 4 minus x squared to the 2/3 power. And that's equal to our f prime of x. Well, beautiful. There's 2 things going on here. We want to find out where the derivative equals 0. And we want to figure out where the derivative does not exist, at least for the values for which are in the domain. But everything is in the domain. All values of x are good. So let's set this equal to 0. Well, I know a little bit we can get confused with limits, but the only thing that's going to make this shit equal 0 is the numerator, not the denominator. So next step, imagine me multiplying both sides of this thing by the frickin' denominator, or actually, I don't give a shit. No, only the numerator makes it equal 0. Hence, x is equal to 0. There's our first critical number. Or I'll call it a critical value. X equals 0. We're going to get more. We're going to get more. So we found it for that's the only place that this derivative equals 0. Is it x equals 0? Cool. So why don't we now take this, move over here, and think about, well, we want to figure out now where the derivative doesn't exist. And where the derivative doesn't exist is when the denominator equals 0. You remember domains, don't you? Not allowed to divide by 0. So if we can find those values of x such that the denominator equals 0, well, then we would find out where the derivative does not exist, and we can go get our last critical values. So why don't we just take the denominator and set this equal to 0 and find out where these values are all jacked up. Divide by 3. Hit it with a 3/2 power on both sides. Do a difference of squares. Or try and remember your plus or minus when you do this, when you hit it with a square root. We're going to find out x is equal to plus or minus 2. Plus or minus 2, and there's our values. We've now found them all. That's it. X equals 0 and x equals plus or minus 2 are our our 3 critical values. So the 0 coming from the numerator equaling 0, and that would have been our f prime of x equaling 0. And where it doesn't exist, well, shit, that's going to be at 2 and negative 2 because the denominator can't equal 0. Let's go tackle our next problem. So here we have g of t is equal to 3 times t minus sine inverse of t. Now, to start off, now all of this crap we had back here, let me just bring you back to the little PowerPoint, if it'll come through. It says, a critical number of a function is a number c in the domain. It's got to be in the domain of f, what we start with. So let's go back to it now and look. Let's talk about the domain. 3t, we're good to go. But sine inverse of t, that's meaning that all of our values need to be trapped between -1 and 1. Okay? We need to be trapped between -1 and 1. So we're only looking for values of values of t, my bad, that are between -1 and 1. And we actually don't really care about the endpoints. It's not differentiable there anyway. Do you remember that? That the endpoints is not differentiable anyway, so we're not really going to give a shit about the endpoints. All right. So we're going to want to find two things, where our g of prime of t equals 0 and where our g prime of t does not exist. So let's take a derivative. Let's go. So g prime of t is equal to derivative on 3t is 3, and then the derivative on sine inverse of t is 1 over the square root of 1 minus t squared. Cool. Well, let's start off by setting this thing equal to 0. Let's go solve. 3 minus 1 over the square root of 1 minus t squared. So why don't we add this over? You know, so we have all positives. Multiply over, do some stuff. You're going to find out 1/3 is equal to the square root of 1 minus t squared. A little bit of fancy algebra going on there. We just do a little cross multiplication, then divide shit out. It doesn't matter. Okay, let's square both sides of this sucker. Let's square both sides, and we're going to get 1/9 is equal to 1 minus t squared. Well, let's subtract the 1 over. We get -8 over 9 is equal to negative t squared. Oh, so t squared is just equal to 8 over 9. And when we hit it with a square root, we're going to find out that t is equal to 2 root 2 over 3. You punch that into a calculator, and you're going, oh, shit, I forgot something. Holy crap. When you hit something with a square root, you need a plus or a minus. Dang, look at me being sloppy there and almost forgetting that. Good thing we know about this, the number, both negative and positive 2 root 2 over 3 are within our interval here. So we found our first couple of values. T is equal to plus or minus 2 root 2 over 3. Cool, right? Because this is an 8 over 9 less than 1. So when we take the square root, it's not like it's going to become larger than 1. Now we need to talk about where the derivative does not exist. So let's go. Let's take our derivative and let's rewrite it in. 3 minus 1 over the square root of 1 minus t squared. Okay, I think the 3 is chill. You know what I mean? I don't think that's a domain issue. Yet we would have 2 different domain issues in our second term, right? First off, don't divide by 0, right? Don't divide by 0. And no negatives underneath even roots. But the negatives underneath the even roots are already handled by the domain of sine inverse of t. You'll see that in a second. So really all we're going to do here is we're going to take the denominator, 1 minus t squared, and we're going to set this thing equal to 0 to take a look at it. Actually, you know what? Let's do something different. That's the issue, right? So why don't we just take the radicand out? The thing underneath the radical. Well, first off, we need it to be positive, right? It can't be negative. No negatives underneath even roots. And shit, we can't divide by 0, so this thing better be just greater than 0. Let's do some work. And oh shit, algebra fails us here. Dude, I just wish I knew somewhere where 1 minus t squared was greater than 0. I mean, I guess we could do a difference of squares, and what's that, like a 1 plus t, a 1 minus t, and then we can interval test to figure out, but bro, come on, do you know how to graph 1 minus t squared? It's just a parabola face down, goes up to 1, it's got some intercepts and shit. Oh crap, I think that's telling us. Where is that thing greater than 0? Up top, where the shit's greater than 0. So it's actually, we'd have we would have holes here, because we're not allowed to equal 0 either. So it turns out that we are able to be greater than 0 when t is trapped between -1 and 1. You can interval test too to find this out. Wow, so it's saying that t can't actually equal -1. And t can't equal +1 as well. Hey, and that's in the domain of the function. But they're endpoints. Ignore the endpoints for critical values. It's all going to come out in the wash. The reason being is the endpoints are not differentiable anyway. If it's not in the domain of the function, the endpoint is not differentiable anyway, just by the definition of our derivative. That's why we don't actually give a shit about it. There might be some ambiguity here, but when we're talking critical values, let's make sure that it is not the endpoints. We're just looking for things that are within the domain. So I know this was a very, very tricky one, so the only solution to this problem is right here. Bang, 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 bang. It's just t is equal to positive or negative 2 √2 over 3. And sorry about such a long one. I'll see you in the next.